Welcome back to the channel, everyone. What I'm presenting today is a lesson plan or lesson idea more on linear regression. And I'm using data related to atmospheric CO2. And we'll look at some plots, we'll do some linear modeling, and we'll do some interpretation of the results. So let's get started. The first thing I want to talk about is the idea of education standards. And so if you're interested in using this for, say, an advanced high school course or even for an undergrad course, you should be aware there are some national K-12 standards. And so in a way to present this information, I wanted to connect what I will be talking about to these standards. And there are many ways that that could happen, but I called out a few here. So one of the standards deals with the relationship between input and output. And so we'll be doing some work that directly connects to that. There is a standard that relates to the key features of graphs. So we'll also be looking at some charts that are generated through code, and we'll look at that and see what they tell us. We'll be using technology to generate graphs of functions. So that's definitely connected. And then finally, there's another one about the use of computational representation of human impact on Earth systems. So because of the context of this information, which is atmospheric CO2, and the time period that we'll be examining, we'll be looking to see if we can identify any noticeable trends in those levels over certain years. And so I think that connects pretty well. Now, the first three of those are related to mathematics more directly, and the last one I talked about is more of a science standard. But, you know, as with most things, there is this interdisciplinary approach that you could take. So as far as the specific data, there's some information that I got from NOAA, which is the United States Atmospheric Science Group. And so they presented some information taken from ice core data. So the values that they presented were from ice cores. And so that essentially involves drilling a giant, hole through the ice and then pulling out the long tube of ice and then looking at slices of it to determine the amount of CO2 in each slice. So through some calculations, they were able to present numbers related to the CO2 at those different years. And some of it was more recent, taken directly after we started to actually pay attention to that and use atmospheric gas sensors. And so through a combination of methods, there's an assembled data set that goes back a very, very long time. So that's what we're using as the basis for this. And as far as goals, I think this is something where we can look at really learning how linear modeling works and how we can use it for interpretation. But we're also using this to learn a little bit with some hands-on examination of CO2 information, CO2 data. So I have the two data sources here. One is Antarctic cores, revised 800,000 years CO2 data. And so this is the data set that goes back 800,000 years. We're not going to be looking at all of that, but it does exist. And then there's another data set with globally averaged marine surface annual mean data. So that contains the more recent measurements of CO2 data. And in both of them, it should be noted that they're both listing CO2 as parts per million. So when I use the term ppm, that refers to the parts per million of CO2 that was detected. So the first thing that you have to do typically is to clean your data. As far as the R code goes, I'm just loading the entire tidyverse collection of packages, and that includes dplyr, which is used for some data manipulation. And there's some writing here that I'm just going to skip over, but basically what we need to do is get this into a good position for us to do the linear modeling. So initially I just take a look here. There's a table of what we see here with CO2 ppm and then the age, but I have to sort of adjust that so we get the actual years. And so I'm going to scroll through this a little bit quicker, but what we end up with is a data set that contains the year and the ppm for the CO2 measurement. And that, gives us our final data going back quite far. And so the initial trend here is plotted. We can look at this and just see what we have. And going back to the very beginning, we see that there is some cyclical change in the CO2 levels. And so at the very beginning, it starts around, say, 200 ppm, and it spikes to maybe 275 or so. And then we see that that goes back down and then up and down and up and down and up. And I counted 9 spikes prior to the latest one, which ends in the year 2000 in this data set. And you'll notice that the spikes, you could argue that the first few of them, 1, 2, 3, 4, 5, the first 5 maybe peak around 250, and then the next 4 peak around 275, perhaps, arguable. And then the last one, though, is up around 375 maybe. So that one is definitely a lot higher than the prior 9 spikes that you can see here. So one thing that I would like to do is look at this large spike at the end more directly. So what I'm going to do here in the next step is to filter so that only the last 500 years are included. And so in this case, we can look at this and see that the values are quite steady at around 280 ppm. And then somewhere closer to the year 2000, that starts to go up quite rapidly. And then in the most recent years, it seems to increase its rate quite a bit. So there's a few things I want to point out at this point. We need to recognize that the data are nonlinear. If we look back at this chart, we can see some shift, a little bit of bouncing around, but essentially a linear trend around 280 ppm for quite a while. But then the more interesting part of this chart, obviously, is where this starts to spike. And that is a curve. And so, a single line would not suffice to model this trend for all of this information. There seems to be a sharp rise in the ppm values after that long flat trend. So we can see essentially, if you wanted to say there are 2 distinct trends, I think you could say that, and there's sort of an elbow in this data. And the sharp rise seems to be roughly exponential, starting in perhaps 1800 or so. This particular chart doesn't have the years with a lot of detail. There's only 4 values here that are shown, but I think that's around 1800. And again, with that curve, it makes me think that it could be an exponential trend. I do want to point out very clearly that correlation is not causation. So we'll be looking at perhaps a reason, why we're seeing this trend. But I want to be very clear in that and just say that correlation is not causation. So I'm not making any causal determination here. But to the point of what could be related, it's important to note that the Industrial Revolution, which is where humans started to make things with machines and factories and use a lot of fossil fuels to drive that. A lot of coal and oil were used to drive those processes. That period of time is roughly aligned with the late 1700s to the mid 1800s. So somewhere around the time in this chart where we start to see that increase in CO2. However, it's not fair to say that that is a cause just from this analysis. So with that said, though, I want to restrict the data that I look at to that spike. So starting at the year 1850 and then onward toward the year 2000. So the spike part of that chart we just saw. And so now we get into linear models, and our goal will then be to look at that restricted range of data and then see if we can determine some linear models from it. So looking at the chart here, we see that we start at 1850 and go to 2000, and it looks like we were able to successfully capture that bend. So from 1850 to maybe 1960 or so, there seems to be a somewhat linear trend. And then around 1960, there seems to be that bend. And then upward from there, we see another roughly linear trend. So the big picture shows a nonlinear trend, but in this very restricted frame, it looks like we could be justified in having two linear models. So for the purposes of this lesson idea, that's what I'm going to do. There could be another model that would be better. That would be a nonlinear model. I'm just going to restrict this to two linear models to try and compare two different periods of time before and after 1960. So the first thing to do is to split the data into those two different periods. So I'm using a filter technique, a filter method from, I think it's from dplyr, and that will give us the years before 1960 and then including and after. So I'm just using year, the year variable is less than 1960, or it's greater than or equal to 1960. And then base R contains the LM method here. So I'm using that to generate a linear model, which is what LM stands for. And the way that you set that up is you have here the CO2 values listed first, and then a tilde, and then the year. So that's where you declare that the ppm value is influenced by year. And you could have other variables too if you had that in your data set. And then the data, I just have to specify which of those two data sets I'm using. And so this is using the pre-1960 data set for the pre-1960 model. And then I do the same thing for the post-1960 model. And the next thing to do is look at the summary of these models. And so the summary information is a bit complex if you're not used to it. But what I want to point out are the low p-values. And those are generally indicative of your model quality, just to state it very broadly. And I got this nice quote from Jim Frost. He has a nice channel where he talks about statistics. If the p-value for a variable is less than your significance level, your sample data provide enough evidence to reject the null hypothesis for the entire population. Your data favor the hypothesis that there is a non-zero correlation. So there's a lot in here, and we'll look at that, but the p-value is generally compared to a significance level, often 0.05, and so we're going to see if it is below that value. And the sample data in this case are the data from the scientific measurements. And the null hypothesis is this idea that everything is the same in this case. That there's no influence of year on the value of CO2, and the entire population in this case would be all the real values in the world that were the ones that were measured and all the ones that were not measured. So in this case, what we're looking at is the relationship of year and CO2, and the initial null hypothesis is that there's no relationship. And if the p-value is very low, then it indicates that there is support for that relationship to be present. So here's the summary for the pre-1960 model. And something to look at here, first of all, we have an intercept value, and we have the estimate, which is associated with the year variable. That is the slope. And if we look at both of these, we see a very, very small p-value. Now, it's written in scientific notation, but this is very small, and these 3 stars after that indicate that it's highly significant. And if we look at the r-squared values down here, that is very close to 1, which indicates that the data lie more or less on the line. And so that's good. That suggests that the data are linear in the way that we modeled them. And then finally, the p-value for the whole thing looks pretty good. So generally speaking, that looks like a decent model. For the post-1960 data, we again have our intercept and slope over here, and the p-values are low, and the r-squared value is high. So that's good. An important part of this, I didn't talk about assumptions for linear regression, but there are some. You want your data to be good quality coming in, and that way you can have a good model and good conclusions. So, what I want to do here briefly is take an aside and do a quality check, and there are a few different ways to do that. The first one is to look at residual plots. So the residuals are just the distances from each data point to the line of best fit, which is generated in that linear model. And we haven't seen those lines yet, but essentially the distance that those data points are away from the line of best fit are the residuals. And you can take those and analyze them to see if your model and your data are good. So here we see a residual plot for the pre-1960 data. They're generally scattered somewhat randomly. There's a few high ones over here, but they look okay. I don't see any super obvious trends in there. And then below here is the post-1960 data. That looks pretty good too. There aren't a lot of data points. There's maybe you can imagine a line there, but they seem to be scattered relatively well, which is what you're looking for in these plots. QQ plots are another type of way to look at your residuals, and this way you can see if they follow a normal distribution. And the way that these work, you want to see that they are aligned on this line. So generally, there's a little squishiness. I don't know, it's a little weird on the edges typically, but these seem to be okay. They lie close to the line in both the pre and post. This one's a little bit worse, but it's okay, I guess. And then as far as the density plots, you can also do a density plot of your residual data, and these should approximate a normal bell curve. And so they should look kind of like this. And of course, with real data, they will never look perfect. But what we're looking for is something approximately like a bell curve, and I think that's okay. So with that in mind, I think that everything looks fine. And as far as viewing the models, what I wanted to do was take the line of best fit from each of those linear models that were created and plot it on top of the data points. So here we do that, and you can see that the 1960 break is where they intersect. So the red line indicates the model for the pre-1960 data, and the blue line on the right indicates the model for the post-1960 data. And it looks pretty good. And I knew that because the R-squared values were high, but it's nice to see it here. Now, to talk about the models themselves, generally, just from the very simple line equation, y equals mx plus b, it's also listed here as y equals beta naught plus beta 1 times x plus error. And here in this context, the y is being estimated. That's in our model, the estimation is for the amount of CO2, and the x represents the year. So for any given year, what is the CO2 estimate? And then the slope is the beta 1, and the intercept is the beta naught. So that's what we're looking at. We're going to see our model in this form shortly. So to get that information, we can extract the coefficients from our model. And so if you simply refer to your model and then use that $sign to access the variables and then get to the coefficients, you can store that and then look at them. So I'm pulling the coefficients out of each model, and then I'm using some text manipulation to really just write that in a statement for us. And so you can see here that I'm accessing some of the values inside of the coefficients. Some of the terms are rounded. And so this gets pasted into a statement. So pre-1960, our model is y equals negative 283.67 plus 0.31 times year. And then for post-1960, it's negative 2083.11 plus 1.22 times year. So we have these two models now. Those are the equations for the red line and the blue line that we saw in that previous chart. And So looking just at these numerically, we can see that the slope is quite different. I want to focus on that for the remainder here. So in the pre-1960 line, we have a slope of 0.31, and in the post-1960 line, we have a slope of 1.22. So what does that tell us? This is kind of the point of this lesson, is to get those values, number one, and then two, to interpret those values in the context of the science and what we're talking about. So to get at that, I have a list of guiding questions. First, I want you to think about what a slope of 1 would represent. So for every year that you increase, the CO2 would go up by 1 unit. But here we have a slope of less than 1. It's 0.31, or close to a third. And then here we have a value of 1.22. So how do these compare to a value of 1 for a slope? And does the slope value pre-1960 indicate a faster change in parts per million or in year? So which one of those values is moving faster to generate that 0.31? Does the value of the slope in the post-1960 equation indicate a faster change in ppm or year? So same question for each of those models. Then are the slope values positive or negative? And what does that indicate? And then finally, do these results indicate any causal relationship between the variables of year and ppm? So I'll start there and go backwards. So no, there's no causal relationship here. This is not that type of study. Again, we're not looking at that. We're simply trying to model these results and understand their relationship. Are the slope values positive or negative? Well, in each case, these are positive. So we have 0.31 and 1.22. So the slope value being positive indicates that for every increase in the year, there's an increase in the CO2 level or concentration. So then we look at the slope value post-1960. Does that indicate a faster change in ppm or year? Well, in order to get a value over 1, the numerator has to change faster. So the CO2 concentration, or ppm, is changing faster than the year. And so that means in realistic terms, in less than a year, that has changed quite rapidly. So it's changing at a faster rate than the year for every year in that period. And then does the slope pre-1960 indicate a faster change in ppm or year? Well, in this case, it's below 1. And so that indicates a faster change in the year. That means you can go several years before you see an increase in the CO2 level by 1 unit. So that is the lesson, and I think it's a good thing to talk about in mathematics as well as in a science classroom. That's why I included those education standards from both sides. I would love to see some of this information looked at mathematically in a science classroom or in a math classroom. I'd love to see that applied case where you can not only talk about the way that these lines of best fit are formed, but what it means in the context of the science that underlies the data. So I hope that was useful for you. I really enjoyed talking about this, and I'm including this as an example, but also more directly, like I said, as a lesson idea, so you can use it to teach this type of information in your own situation. So thanks again. I appreciate it. And if you enjoyed this content, please subscribe to the channel and give this video a thumbs up. And then if you're interested, I also have a Buy Me a Coffee link down below if you want to show some support to the channel. And other than that, have a great week. Thanks. Bye.